Lesson 5.3 is arithmetic sequences and series. I would pause the video and write down these notes. A sequence is a list of numbers arranged in an order that obeys a certain rule. They can be thought of as a function that maps positive integers, so 1, 2, 3, 4, 5, so on and so forth, to real numbers, where we use the notation u sub n or a sub n or some letter sub n, which is equivalent to u of n, like function notation. So u is your y value, n is your x value. Term is each number in the sequence. The nth term is where n is a positive integer, n is equivalent to your x value. Then you can represent the nth term as u sub n, that's equivalent to your y value. The first term is the first term in the sequence, which we represent with u sub 1. An arithmetic sequence is a specific type of sequence where the difference between each term, or one term and the next term, is constant. And we call this difference the common difference, which we use the letter d to represent. So that's the constant difference between each term in the arithmetic sequence. It means you're adding or subtracting the same value every single time. So to get from one term to the next, you're always adding or subtracting the same value. The way that you find that value is you just take two terms and you subtract the later term minus the term before it. So for example, the second term minus the first term, or the nth term minus the n minus 1 term. So here we have two sequences. The first one is 2, 4, 6, 8, 10, so that means that same pattern continues forever. And we want to do two things. First thing we want to do is write down a general formula for the nth term, so that's like your function, what's your formula, your equation, and then we also want to find the nth term. So when you have this sequence here, it's just a list of numbers, but this is saying when n is 1, your term is 2. When n is 2, your term is 4. And so these are your x values. So you can kind of think of them as like coordinate pairs, like x is 1, y is 2, so you have the coordinate pair 1, 2. X is 2, y is 4, so you have the coordinate pair 2, 4. X is 3, y is 6, so on and so forth. So using that, write down an equation or a general formula for the nth term for this pattern, and then find the 12th term. So for this first one, whatever your x value is, your y value is always twice that, or whatever your term number is, the term is always twice that. So the first one, u sub n is equal to 2n. So this is just like kind of like a linear equation, except for we're just writing it in sequence notation instead of function notation. And then the 12th term, you just plug in 12 for n because that's your x value. So you end up with u sub 12 is 2 times 12, which is 24. So see if you can do the same thing for number 2. Find the pattern, write it in terms of your x or your nth value, and then find u sub 12. So for this one, every single time it's just 1 divided by whatever n is. So u sub n is 1 over n, so therefore u sub 12 would be 1 over 12. So this is a sequence, just a list of numbers. They follow a pattern. A lot of times you can create a general term for this pattern, and then you can find a specific term in that sequence. When you're finding an nth term in an arithmetic sequence is exactly the same thing as a linear function. The only difference is the domain is only the positive integers, so 1, 2, 3, 4, 5, instead of all real numbers. So when you're finding the nth term, it follows this pattern. U sub n is equal to u sub 1 plus n minus 1 times d, where d is the same thing as your slope, m, or your gradient. And then this is exactly the same thing as point slope form, where u sub 1 is your first term, or the y value when x is 1, and then n minus your x value, which your x value is 1. So this is just point slope form, but we just call it nth term of an arithmetic sequence. So they give us some information here. They tell us that the first term of the arithmetic sequence is 5, and the common difference is 2/3, and we want to find all of these things. So we want to find the second and the third term. So remember, this is your first term. This is when x is 1, y is 5. And then our common difference is what you're doing every single time. So if the common difference is 2/3, that means you're adding 2/3 every single time. So go ahead and pause the video and do parts A and B. So if our first term is 5, if I add 2/3 to it, that means our second term is 5 and 2/3, or 17 over 3. And then if I add 2/3 again, that means our third term would be 6 and 1/3, or 19 over 3. So those are our second and third terms. I just added 2/3 every single time. And then the nth term, or the expression, so I just plugged everything into here. U sub 1 is our first term. N is just n. That's like our x value, or just x is x. and then d is 2/3. I don't really like writing this on the end. I usually flip it and write this in the beginning just like we would on a linear function. So u sub n is equal to 5 plus 2/3 n minus 1. So for part C, we want to determine whether or not 49/3 is a term of this sequence. So a term is a y value. So basically, if we plug this in for y, will this actually work? And the way we know whether or not it works is our n value must be a positive integer. So it must be 1, 2, 3, 4 on forever. It can't be a decimal, it can't be a fraction, it can't be negative. So go ahead and plug 49/3 in for u sub n and figure out whether or not this works. So if you plug in 49/3 for u sub n and then solve for n, subtract 5 from both sides, you get 34/3 equals 2/3 n minus 1. So then I multiplied by 3/2 to cancel off the 2/3, and you end up with 17 equals n minus 1, so n is equal to 18. Because this is a positive integer, that means that the 18th term in the sequence is 49/3. So yes, it is a term in the sequence. Last part, find the first term in this sequence that is greater than 25. So you want u sub n to be greater than 25. Pause the video and try this one. So I took the general term, or the nth term, 5 plus 2/3 n minus 1, and I set it greater than 25, and I solved for n. And I found that the 31st term is 25. So if I want the first one that's bigger than 25, I found the 32nd term. So I plugged in 32 in for our nth term, and I found that the first term that's bigger than 25 is the 32nd term, which is 77/3. So whenever you're doing arithmetic sequences, just always keep in mind that they work exactly like linear functions. The common difference is the same thing as your slope, and the first term is the same thing as like when x is 1, what is y? Your term number, so 1, 2, 3, 4, 5, those are always your x value, and then the term itself are the y values. So now we have an arithmetic sequence that starts off as -3, 5, and then it continues on, and then it ends at a 1189. So the fact that it stops, this means that it's an ending sequence, it's finite. So we want to find the common difference, and then we want to figure out how many number of terms are in this sequence. So go ahead and pause the video and try that. So the common difference is what are you doing every single time? So to get from -3 to 5, we added 8. Or if you want to do it the way that the formula, 5 minus a -3 plus 8. So then I wrote down the general term for this, or the nth term. So u sub n is equal to -3, the first term, what you're doing every single time, so plus 8 times n minus 1. And then I wanted to figure out how many terms there are, which is the same thing as asking what is the x value when your y value is 1189. So I set u sub n equal to 1189, and I solved for n and got n to be 150. So there are 150 terms in this sequence. Here are some notes on arithmetic series. I would pause the video and write down these notes. A series is a sequence whose terms are being added, so therefore an arithmetic series is an arithmetic sequence whose terms are being added. This is sigma notation. It represents adding up, or the concept of summation. So this is the capital Greek letter sigma. We also use this s sub n to represent series or summation. And so what this is saying if this is your nth term, like u sub I represents the nth term or the general term, I is where you're starting. So I'm starting from the first term, and n is where you're ending. So I'm summing up the sequence represented by u sub I from the first term up through the nth term. And that just literally means add up all the terms. So we have a formula for the sum of an arithmetic series. It's the same thing as the area of a trapezoid, actually. So if you want to sum up the first n terms of an arithmetic series, it's n divided by 2 times the first term plus the last term. You don't always know the last terms. You can find it using your general term, but it's the same thing as the n divided by 2, and then it would be 2 times the first term plus the common difference times n minus 1. Because u sub 1 plus d n minus 1 is u sub n. So if I just substitute that in, these two are equivalent to each other. So on this example, we have a arithmetic series, 60 plus 57 plus 54 plus ... And we want to sum up the first 20 terms. So go ahead and pause the video and do that. So this is the summation notation of this arithmetic series. I have n, I just used n because that's the letter we use for sequences, is equal to 1 because we want to sum for the first term up to the 20th term. And then I wrote out the general term, so the first term was 60, the common difference is plus 3, so 60 plus 3, n minus 1. So you can actually do these on your graphing calculator. If you go to math and then go to 0 summation, you just type in it exactly like this, except for instead of n, use the variable x button, and then the calculator will actually do the summation for you. To do it by hand, I just used the arithmetic series formula, and since I didn't know the last term, I used the one that was 2 times the first term plus the common difference times n minus 1. So n was 20, the first term was 60, and the common difference was 3. Plug all that in my calculator, and I end up with the sum of the first 20 terms is 1,170. So here's the second one. We have negative 10 plus negative 6 plus negative 2 plus dot 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 plus 90. And we want to find the sum of the arithmetic series. Notice we don't know what n is, so you'd have to find what n is. And then find the least number of terms if you're given this series without an n value that makes the sum greater than 100. So go ahead and pause the video and try number 6. So the first thing I did is I figured out how many terms were in this series. So I set 90 equal to the general term. Our first term was negative 10. We are adding 4 every single time times n minus 1. And I found that n was 26. So then I plugged it into the arithmetic series formula where I knew the first and the last term. So 26 over 2 is equal to negative 10 plus 90, which is 1,040. If you used your graphing calculator, the math summation, you would have had to plug it in as x is equal to 1 up to 26, and then your general term of negative 10 plus 40 times n minus 1. So for the next one, we want the sum, so n over 2 times negative 10 plus 4 times n minus 1 to be greater than 100, where we're needing to solve for n. So that's why I use this version. There's a few ways you could do this. You could do this by hand if you know how to solve quadratic inequalities by hand, or you can use your graphing calculator. So there's a few ways to use your graphing calculator. One way is to go to y equals and type in the general form for the arithmetic series under y1 using x instead of n. And then you can actually use your table function. So if you go to second window, which is table set, you want your delta table, so that's how many x values it goes up by, to be 1, because in a series or a sequence, your n's can only go up by 1. And then your table start, we know that at n equals 26, it's over 1,000, and we only need it to be over 100. So I would say maybe like 5 or something like that, something small. And then once you have that set up, go to second graph, which is table, and you want to look at the y1 until you have a y value that's bigger than 100. So if you look at the table, it says that x, or in our case n, when n is 10, y, which is s sub n, is 80. When n is 11, s sub n is 110. So 11 terms is the first time that this sum is greater than 100. These examples are a little practice with our summation notation. So we have a summation here that says the sum from n is 1, or they're using I is 1 up to 4, of 2i plus 3. So this is your formula, and we're going from the first term to the fourth term. So we want to write this as an expression of a sum of terms, so something that looks like this. So I found the first term here. I just plugged in 1 for I and got that to be 5. You want to do the same thing all the way up to 4 and then just write it in this type of expression. And then once you've done that, actually calculate the sum. So go ahead and pause the video and do number 7. So u sub 2 is 7, u sub 3 is 9, u sub 4 is 11. So writing it as a expression of a sum, it'd be 5 plus 7 plus 9 plus 11. So then the actual sum, add them all up or use your graphing calculator, you should end up with 32. So now we're going the other direction. Here we have the series written as a sum of numbers, and write this using sigma notation. So go ahead and pause the video and try that. So sigma, we're starting at I equals 1. There's 6 terms, so we're going up to the 6th term. Our first term is 1. Our common difference is plus 2, so 1 plus 2i minus 1. If you want to simplify it, it'd be 2i minus 1. This is like point-slope form versus slope-intercept form. They're equivalent, just different ways to write it. And it doesn't matter what letter you use. They always use I, but as long as you're consistent, if you put an n here and this is an n, as long as whatever one you put inside here is the same as what you put in the sigma notation. Another application of arithmetic sequence and series is simple interest. So interest is money paid by a borrower when money is loaned. So for example, if you are putting money in a savings account, you're technically loaning it to the bank. that's why you earn interest in a savings account. Or if you borrow money for like a mortgage or a student loan or something, that's why you pay interest. Capital or principal is the initial amount in the savings account or that's loaned. So simple interest is that you just earn or pay interest based on whatever the principal is or the capital every year or whatever the time period is. The way that you calculate simple interest is that it's your capital times your interest rate times how many ever years. So this first example says that an amount of 5,000 UK pounds is invested at a simple interest rate of 3% per annum, which means per year, for a period of 8 years. So calculate the interest received after the 8 years and find the total amount in the account after 8 years. So you have the interest, which is what you're earning, and then how much total is actually in the account at the end of the 8 years. And then the next one says that Riddy invests $4,000 into a bank account at simple interest rate of 7.3% per year. Find the number of years it takes for Riddy's money to double. Let's go ahead and pause the video and try those two. So for the first one, interest, calculated principal times interest rate times the number of years. Make sure your interest rate is in decimal form. So 5,000 times 0.03 times 8, which is 1,200 pounds. So over the 8 years, you'll earn 1,200 extra pounds in interest. For part B, total amount of money, well, you have your principal, the 5,000 plus the interest. So therefore, at the end of the 8 years, you will have 6,200 pounds in the bank account. Last one, if you're investing $4,000 into a bank and you want it to double, that means you're going to end up with $8,000. So I set that equal to the initial amount plus what you would earn in interest, with t being time because that's what you're trying to solve for. So subtracted the 4,000 from both sides. Basically, you want the interest to be equal to 4,000, and then I divided by 4,000 times 0.073, and you end up with 13.7. But since we're earning interest per year, that would mean after 14 years, your money would double. So this has been arithmetic series and sequences along with simple interest. Just keep in mind that they act exactly like linear functions, it's just a slightly different notation.